Hello students, I'd just like to show you two more examples dealing with dimensional analysis. The first example deals with solution concentrations. If you are ever given a percent composition, that will be a mass ratio. A percent comp is a mass ratio unless otherwise told. When you purchase any kind of vinegar in the grocery store, it's a 5% acetic acid solution. Now, what that means is there are 5 grams of acetic acid per 100. Now, to respect sig figs, this would be 1.0 times 10 to the second grams of the solution. Now, a solution is a homogeneous mixture made of a solute, in this case acetic acid, dissolved in a solvent, which is water if it's a liquid solution unless otherwise told. Now, if it's a percent and not a mass ratio, you will be told that. For example, you may have a 38% sulfuric acid solution by volume. Then what that means is there will be 38 units of volume, let's just say milliliters, of H2SO4 for every 1 times 10 to the second, or 100 milliliters of the solution. Now, you could reference these both liters, etc., because it's a ratio. Now, there are other, of course, expressions of solution concentration: molarity, molality. We're going to learn this year normality, mole fraction, but coming into AP, it's the expectation that you'll just be familiar with percent comp. So, let's dig in. A 37% hydrochloric acid solution. I'm going to go ahead and just create that as a conversion factor. A percent is a mass ratio unless otherwise told. So this means I have 37, 3 sig figs, grams of HCl for 100 grams of solution. Calculate the mass of the solution, not the mass of the HCl, but what delivers the HCl, which is the solution, in grams, if 250 milliliters of the solution was reacted. The density, that's good to have. The density of the solution is 1.19 gram per milliliter. Now, because I know I'm using dimensional analysis, I'm going to expand the density to be a conversion factor also. So, I've made a conversion factor. My density is a conversion factor. I know I need this as my answer. This is my given. So, 250 milliliters of my solution. Now, I know I don't want mils. I want mass in grams of my solution. So I know that milliliters of solution. Now, do I know, can I get to grams of solution? With the density, there's 1.19 grams in every 1 mil. That did it. Since I was given density, that's all I needed. I didn't even need to use the mass ratio. Now, I must say, in chemistry, there's very, very rarely any extraneous information given. But in this case, there is. So, 4 sig figs, 3, so I'm only allowed to report 3, and the answer will be 298 grams of the solution. Now, length cubed is volume. So whenever we see a metric or an English unit of length that is cubed, we cannot forget that's an expression of volume. So, what this question is asking me to do is to convert what we normally see as a unit of volume, liters, to volume as length cubed. Whenever we're asked this or given this, I always remember and remind myself of a cc. 1 cc, that is a cubic centimeter. That is equivalent to 1 centimeter cubed, which is equivalent to 1 milliliter. I'm probably going to use this somewhere. In fact, if I go from liters to milliliters, and that's a quick conversion, I know that relationship. Well, milliliters convert me to centimeter cubed, and doesn't that look a heck of a lot closer to kilometer cubed than what I started with, liters? Now, I'm in length expresses volume because it's cubed. But can't I go from centimeters to meters to kilometers? Well, couldn't I just make the leap but just remind myself that it's cubed? So if we remember, what we'll do here is first get myself to mils. 1 liter, 1,000 mils. By definition, does not limit our sig figs. And for every 1 milliliter, it's 1 centimeter cubed. So it would be fine if you went ahead and put 1,000 centimeters cubed here. Now, this is the way that I would write the equivalent relationship. All right. Well, now, technically, I need to cancel centimeters cubed and get myself to meters cubed. I know these beyond a shadow of a doubt. We use conversion factors from our memory when there's no hesitation of the relationship. This quickly comes to mind. Now, we may want to write 100 centimeters cubed in 1 meter cubed. That is the one-dimensional relationship. There's 100 centimeters in 1 meter. There's not 100 centimeters cubed in a meter cubed. Now, I know this relationship off the top of my head. I do not know how many centimeters cubed are in how many meters cubed off the top of my head. But can't I use the relationship that I know and the math skills that I know? So couldn't I cube this entire expression? No, that's why I pointed out. See, the cube here is on the unit to establish this relationship. But here, I need to put the cube on the outside. We just can't forget to apply the cube to the numbers when we're doing our math. So I'm going to use that same relationship here to eventually get me to, that same technique to get me to kilometers cubed. I know this beyond a shadow of a doubt, but I'll need to cube this to be able to cancel the meters cubed and then leave me with kilometers cubed. Just be so careful when you're doing your math, especially in your graphing calculators. Take as many steps as you need, and we will get 3.3 times 10 to the minus 5th kilometers cubed. Good luck. As always, if you have any questions, please do not hesitate to email me.